Thanks, Barbara. It's great to be here. You're all my friends, so I don't really think I should be lecturing, but we have the microphone and I'm supposed to stand here. And so I'll try to tell you a little bit what I know about our climate change, both globally and near to Iowa, along the lines of the report, which we just mentioned and we'll talk about tonight. My wife said this is in the UI Explorers series, which I'm very grateful to be a participant in, but my wife said, you don't look like an explorer. She said, you're no explorer, so, okay. Is it more convincing now? Okay. I don't think I can do that, though. Okay, climate change near and far. This is the planet in which we're trying to protect, and I guess as you know, when we talk about climate change, we're not talking about weather. We're not talking about the day-to-day change in weather or hourly change in a storm. Rather, we're talking about decades, centuries, millennia. And you might think that even a decade, 10 years, is the smallest data point that we might think about in terms of the long-term interest in climate change. So having said that, it's hard to talk about the climate in Iowa from any type of a human experience or instrumental measurement because our recordings aren't very long. We have geologists who help us with a stratigraphic record and try to interpret what has happened in the past. And we're not going to talk too much about that tonight, but that's a very important part of the entire story. I'm going to show you no models tonight whatsoever, only data, because I think the data is compelling enough. Data from multiple lines, from space, from surface temperature measurements, from ocean platforms and buoys, from mobile ship measurements, from down boreholes in deep wells, from the ecology and paleographic literature, we know an awful lot as well. All these lines of evidence make somewhat of a consistent story. I'd say it's not perfect. We certainly don't understand everything there is to know about climate or climate dynamics, but taken in sum total, I think it's rather convincing. This is one of the pieces of data here. It's the two different groups in East Anglia and Goddard Institute for Space Studies in New York City put together surface temperature records independently, and they're shown in the bottom slide here. And the top one is the graphical geospatial depiction of that data. And the darker the red color, the hotter the temperature it is over this 150-year record that we're looking at of surface temperature measurements. And first thing you might see is that in 150 years, it's significantly warmer. It's about, on average, 1.4 degrees Fahrenheit warmer. The other thing you notice right away is that it's much warmer in certain places, like the Arctic. The models, though we're not talking about the models tonight, they do get that part right because it's a positive feedback loop. As the ice first begins to melt, the skin of the Earth is a little bit warmer from the greenhouse gases. As the ice begins to melt, it yields a white reflective surface to a dark sea. That melts more ice, more absorption of radiation, and so on in a positive feedback loop. And so the models do get that part right, and it is much warmer in the Arctic, as you can see. The other thing I might mention with this particular record is this part right here. Most climatologists feel that what's happened in the last 30 years is really the emergence of the signal for greenhouse gases that may live long in the atmospheres, 100 years and longer. It's really now that they're beginning to kick in this 30 years. And at this most rapid rate of ascent in temperature is an indication that we're now beginning to really experience the effect of the warming from these greenhouse gases that are accumulating in the atmosphere. One of the most remarkable things I tell my students is that I have them calculate the mass of the atmosphere and the mass of the top couple meters of living soil and the mass of the oceans, because it's a very telling calculation. You rapidly see the oceans are immense and huge, and the atmosphere is relatively small, by the way. You'd expect to see the effects of all the billions of people that we have today, 6.8 billion people, and the increased economic activity. You'd expect to see it in the atmosphere first, and indeed we do. But I would have never guessed that we'd be able to change, in our lifetime, change the whole ocean. But we are, and it's very sobering if you think that, of course, again, it's consistent with the atmosphere. The ocean, if you smear this record over the whole thing, it's about 1 degree Fahrenheit warmer. So it's lagging the atmosphere, so it's a top-down warming. The atmosphere is warming first. It's about 1.4 degrees Fahrenheit warmer, remember. Now the ocean sea surface temperature is about 1 degree Fahrenheit warmer. What's more, we can see the record easily in the Atlantic 700 meters down. And again, it's a top-down warming. It couldn't have happened due to changes in ocean circulation. Rather, it must be that the surface of the Earth, the atmosphere, has warmed first, which is again consistent with the greenhouse gas hypothesis, and down from there. It would take thousands of nuclear power plants running hundreds of years, dumping all of their heat in the ocean to warm it 1 degree Fahrenheit like this. This is an immense, immense amount of heat storage already. One problem, of course, is that the emissions continue to rise, and as long as the emissions continue to rise, I think this is lost on many economists and others. The problem just keeps going on. It just keeps getting warmer and warmer and warmer for centuries. There's no reversal until you reverse these fossil fuel emissions. And the curve shown here is the original 1990, I believe, prediction by the United Nations program, the IPCC, the Intergovernmental Panel on Climate Change, of different scenarios. They tried to bracket anything that could possibly be possible, but they missed even on the scenarios constructed. Our emissions have grown much faster, or faster even than any of the scenarios imagined back 20 years ago by the IPCC. Because the skin of the Earth is beginning to warm, and 1.4 degrees may not sound like too much to you, you have to ask, well, what are the impacts so far? This is the climate change far we're talking about now. And one of the climate changes far is the Arctic and the melting of the ice. And this is sea ice that's floating, so that doesn't affect the sea surface level, the elevation of the sea, but rather it does affect the animals who live and make a living off of the Arctic, like the polar bears. So this loss of ice affects the temperature, as we mentioned. It affects the species and the animals, as we mentioned, but not the sea level. The ice has opened up enough that people are very keen to explore now for oil and minerals and things like that, and there's at least 3 countries already fighting over those rights. Ironically, burning of fossil fuels has opened up more area for exploration of fossil fuels. One of the things that is obvious about this is that the Arctic sea ice is melting. We've had pretty good satellite observations of many of the things I'm showing you since 1979. That is in jeopardy, actually. Our Earth observing satellites, we've had 2 failed launches, and the funding for it is in jeopardy, which is maybe another story. But the Arctic sea ice is melting much faster than any of the models or anyone would have predicted. And we don't know why. As I mentioned, we don't understand everything, but the data taken as a whole makes a fairly consistent picture. One hypothesis here is that the particles from cook stoves and from burning emissions even biomass burning, natural fires and so forth, have caused black carbon to go into the Arctic, for example, settle on the snow, and that's not in the models. It's not in any of the models. So that has caused the ice to melt much faster. Just one hypothesis. Greg Carmichael in our center is very much involved in working on this hypothesis and had a paper in Nature on it. This is a view, I didn't take this picture, I borrowed it, but this is a view from Greenland, the heart of Greenland, actually in 2007. This is fairly typical of the meltwater. And they call it a moulin. It is a deep shaft of water dropping down, and the concern is that it could lubricate the ice, Earth, ice, Greenland interface and cause ice sheet to fall off faster. And there's some indication that the rate has increased, but nothing dramatic so far. Certainly the melt rate itself, that which I showed you, the liquid water, it's equivalent to about half a Lake Erie each year right now. So to put it into some context, about half of Lake Erie each year is melting off of Greenland alone and adding to the sea surface temperature. So this problem is different than the Arctic ice that we showed earlier, because this does affect sea surface temperature, most definitely, sea surface elevation, most definitely. The melt area is shown in this slide, and you can see there's a lot of noise in the data, so don't get too concerned about any given year. 2008 and 2009 were a little bit cooler, but the trend is really clear that the melt rate is continuously increasing. This is again satellite data and quite accurate since 1979. Have the ice sheets begun to fall off of the continent faster in addition to the liquid melt rate I showed you earlier? There's some indication, but I think the verdict is still out on that. This is one of the ice streams off the coast of Greenland. Similarly, we are concerned about Antarctica. Antarctica, the ice shelves in Antarctica are again balanced on the continent of Antarctica, but hanging into the ocean. There the concern is, so they won't, when they fall off, they won't exert much of a sea level effect, because most of the weight is being borne by the sea rather than by the continent itself. But there is the concern that once those fall off, you have a much more rapid gravitation of the sheet itself into the ocean with increased sea level rise. We call that, it's actually not much talked about in the United Nations reports, probably should be. It's called abrupt climate change, the notion that ice sheets could move quickly within, say, years and fall into the ocean and raise sea level maybe 10, 20 meters, something like that, 30 feet or more. The reason it's not talked about much in the reports is because it's really a probabilistic calculation. We think that the probability is small, but the consequences are very great. I think we should still find a way to somehow deal with that. There is evidence that especially Western Antarctic is, in general, the continent is gaining ice in this case, unlike Greenland. But that western edge of it is warmer. One hypothesis is that the water is warmer there. I showed it in an earlier slide. And it undercuts the shelves, and that's what's causing them to break off. But I think it's not certain.